Hello everyone from Math 2200, it's Discrete Mathematics. Professor Wenson here again with a video on your ZyBooks Section 8.7. It's titled Recursive Definitions. So we've seen recursive formulas before, earlier in this chapter, how to define a sequence recursively. And that's where, every term of the sequence depends on previous terms. And you had some initial terms, or base cases really defined for you. This is kind of the same thing. This should be pretty familiar. Only instead of sequences being defined recursively, we're just going to have certain objects defined recursively, whether it be functions or binary strings, nested parentheses, trees, binary trees. You'll see all those examples in this section here. Alright, so if you've never seen it before, they talk about the factorial. What does factorial mean? I'm not going to go into that. You should know this. This is another way to this is an explicit way to define factorial. I guess I will get into it. For n greater than or equal to 0, f of n equals n factorial means take n times n minus 1 times all the way down to 1. And 0 factorial is defined to be 1, right? But that's not clear from this definition. A more precise definition of n, the factorial function is given by the following, where you have a basis or a base case basis. F of 0 is 1, right? So you're defined 0 factorial to be 1, and then for every value 1 or greater, every n 1 or greater, n factorial is n times n minus 1 factorial. F of n is n times the previous factorial, f of n minus 1. This second definition here is an example of a recursive definition. In a recursive definition of a function, the value of the function is defined in terms of the output value of the function on smaller input values, right? So it's like the recursive definition of a sequence, where the value at the nth, the nth term is n times the value of the n minus first term, right? The value of one term depends on previous terms. It's very similar to that concept. One can use the recursive definition for n factorial to determine the value of the factorial function on a particular value for n by starting at 0. Multiplying by 0 factorial by 1 to get the value of 1 factorial, then by 2 to get 2 factorial, and so on, until the desired n factorial has been reached. This process is called recursion. Recursion is the process of computing the value of a function using the result of the function on smaller input values. Okay, so you've already done this, something similar to this, with sequences. Right. So for instance, say we're given the definition of a function g whose domain is a set of all non-negative integers, right? So the domain is 0, 1, 2, 3, 4, and so on. And here's the recursive definition of this function g. G of 0 is 0. And then for values of n greater than or equal to 1, right, from inputs of 1 onward, g of n equals g of n minus 1 plus n cubed. And what is g of 3? And again, I'll show you on paper here. This is very similar to what we did with sequences. Okay, so here's this function g again, defined recursively. We have g of 0, and then we can go for n equals 1. Alright, plug in 1 for n. My input's 1 now. Just replace n with 1 throughout this. That's just this rule here. So it'd be g of, and then 1 minus 1 is 0, plus 1 cubed. And we were told, that in this basis up here, base case, whatever you want to call it, basis, base case, g of 0 is 0. So the value of g at 0 is 0, and then 1 cubed is 1, 0 plus 1 is 1. So the value of this function g when the input is 1 is 1. Right. And then keep going, what's g of 2? Right, so just replacing n with 2. And just go through the rule, right? N is 2, so it's definitely greater than or equal to 1. So I go through this rule and just replace every n I see with 2. So this would be equal to g of, and then 2 minus 1 is 1, plus 2 cubed, right? Replacing all the n's with 2. Now g of 1 we found from the earlier line is 1, plus, and then 2 cubed is 8. So the value of g at the input of 2 is 9. And I'll do one more here, g of 3, because they're asking us for g of 3 in the activity. G of 3, just go through the rule, replace n with 3, would be g of 3 minus 1, or 2, plus 3 cubed, and we saw from the line before that, g of 2 is 9, plus 3 cubed is 27, that's 36, right? And there's what they're asking for, right? What's the value of g at the input 3? Be 36. And they go through the rules here with you, just like recursive sequences, right? A recursive function. So I'd leave this one to you. H of 0 is given as 1, and then for values inputs greater than or equal to 1, h of n is the quantity n squared plus 1 times h of n minus 1, right? So the value previously. And then using this recursive definition, what would be the value of h at 2? Alright, and I'll do one more of these. I'll skip the first one, I'll leave that one to you, and let's look at number 2 here. Alright, so in this second activity, we're given a formula, an explicit formula for the function. So here's h of n equals, just n factorial squared. See how the output does not rely on previous values of h, right? If I want, what's the 50th, what's the output at 50? I just plug in 50 here, get 50 factorial squared. What we're asked to do is take this explicit definition, and rewrite it as a recursive definition. Find a recursive definition for this. Now, again, you're going to have a basis or a base case, right? And I'll start off at 0, right? H of 0 would be 0 factorial. Now we already saw 0 factorial is 1, and 1 squared is 1. Okay, so h of 0 is 1. Now I might need more, but let's take a look at, now this is just some scratch work off to the side here. All right. N factorial squared, right? What does that mean? Right? Well, that means n factorial times n factorial, right? It means to take whatever the value of n factorial is and multiply it by n factorial again. Well, we've already seen kind of recursive definitions earlier in this section for n factorial, right? N factorial you could think of as n times and then n minus 1 factorial, and I've got 2 of these. That's the first n factorial, and then the second n factorial I could define the same way. And you see here I've got n times n, that's n squared, times, and then you have n minus 1 factorial, squared, and then this right here, this is the same as h, but instead of n inside, you have n minus 1 inside. So this is h of n minus 1. So you're going to have a basis, which might be multiple steps, but here, since I'm only going back to n minus 1, you only need one base case. If I needed to go back and to n minus 2, n minus 3, I'd need 2 or 3 bases. All right. Then you have your recursive definition. Where I'm seeing here that h of n, right, off to the side here, h of n would be equal to, and then based at what I got at the end here, would be equal to n squared times h of n minus 1. And this is for values of n, greater than or equal to 1 though, right? Because I already put in what it is at 0. There, a nice recursive definition for that function h. Going back here, h of 0 is 1, n squared times h of n minus 1. Perfect. Okay. All right. And again, you do it for the first one. You're given an explicit formula as to write out a recursive definition. Okay, then same concept here. We have recursively defined sets. So we had recursively defined functions. Here's recursively defined sets, and you're just going to see a lot of recursively defined stuff, and they'll all have a pretty similar structure to them. So components of a recursive definition of a set. Again, you have some basis that explicitly states one or more specific elements are in the set. You have a recursive rule that shows how to construct additional elements in the set from the elements already known to be in the set. So from these basis elements, how do we construct more elements? There is often more than one recursive rule. And an exclusion statement states that an element is in the set only if it is given in the basis or can be constructed by applying the rule. Recursive rule applies repeatedly to elements given in the basis. Okay. So for example, you can read that paragraph there. Say, here's a recursive definition of the set of all properly nested parentheses. So basis, the sequence left parenthesis, right parenthesis is properly nested. And then you have your recursive rules. How do you take this basis element and create more elements, more properly, in the set of all properly nested parentheses? Basically, for every left, there's a right. For every left parenthesis, there's a right parenthesis. So here, if U and V are properly nested sequences of parentheses, then putting a left parenthesis and a right parenthesis around that U will also be properly nested, or just concatenating them, just putting them together. Right. And if you're not doing any of this, then it's not part of the set, not properly nested. Right, that's the exclusion statement. So let me show you some examples of what will be considered properly nested then. Okay, so I wrote it out this way. I said, let's let S be the set of all sequences with properly nested parentheses. So again, you have some basis part, some basis step where they give you some elements that belong to the set. So this sequence of parentheses, left, right, belongs to S, is properly nested. Recursive rules, if you have two elements in this set, if you have two sequences of properly nested intervals, parentheses, then just putting parentheses around an element in the set will be in the set, will be properly nested, and just connecting them will be concatenating them, putting them next to each other will be properly nested as well. And then if you're not doing this, right, if you can't use these rules to create your set of parentheses, your sequence of parentheses, then it's not in this set of not properly nested. All right. So I'll just build some other elements here for you. So we already know that this is in here, right? That was given to us in the basis, right, the base case. So if I apply rule 1, right, so I'll call these rule 1 and rule 2. If I apply rule 1, then I take this element that's already properly nested and just throw parentheses around it. So this is also considered properly nested. Right. Now I have two elements that are in this set, and I can apply rule 2 if I wish to two elements in the set. Or I could apply rule 2 to this element twice, because this element belongs to the set I could just put it next to itself. Say left, right, and then left, right again. Just that's the second rule. Just put them next to each other. This is a sequence of parentheses that would be considered properly nested. Right. And then, here's an element. Here's a properly nested sequence of parentheses. Put parentheses around that. And this is properly nested. Same thing here. Take this guy. This belongs to the set of properly nested parentheses. Just put parentheses around it. Apply rule. If I apply rule 1, you could take any element and put parentheses around it, left and right, and that's also properly nested. And again, you can put things next to each other. So I could take this first element here, that from the basis, and then this element that I found, just put them next to each other. And this is also a sequence of properly nested parentheses. And I could do this forever. Right? I could build sequences of properly nested parentheses all day long. Here's one that wouldn't be. If I did a left, right, and took this basis element here, if I just put a left parenthesis on that and left it, that does not belong to S. Right? This is not properly nested. A sequence of properly nested parentheses. And again, just pay attention. There should be as many left parentheses as there are right parentheses. So again, hopefully that makes sense. Again, you can read through all this cap here, watch their animation, see they're applying the rules and all that. So you're asked, is this properly nested? Yeah. You took that basis element, put parentheses around it. Yes, it is. Is this? No, because again, they only added a right parenthesis without a left parenthesis. And this one is because it takes, basis element, puts it next to that basis element with parentheses around it, and then puts parentheses around that. So I mean, they're applying all those rules. We could construct this. You couldn't construct this second one applying those rules. All right. So then they ask you which rule would be applied, to construct the following. Well, here I'd have to apply the first rule, because you would take the basis element, put it next to the basis element, and then apply the rule 1 to get this, right? Here, you'd put these next to each other. That's rule 2. And here, you got this thing next to that thing, and then the parentheses around it. The last step would have been rule 1. And hopefully that's easy to see. And then they do the same kind of thing with binary strings. Here's a definition of how to construct binary strings. And remember that this lambda here was the empty string, right? The string with nothing. Or the string with length 0. Strings are made up of zeros and ones. Remember, hopefully this all sounds familiar. Alright, so I'll write this out and show you how to, just show you examples of how to construct things using these recursive rules. So here's that recursive definition of the set of binary strings. This B star. It's a set of binary strings of any length. Now the basis is that empty string. Right? Remember, this is the string with nothing. The string of nothing has a length of 0. That belongs to the set of strings of any length. And then the recursive rules, telling you how to construct other strings from previous strings. If you have a string in this set, then you just pop a 0 on it, and you get another string, and then or you could pop a 1 on it and get another string, and that's it. And if you can't, if you can't construct a particular string using these rules, then it doesn't belong to this set. So an example, let me build some strings here. So again, the empty string, we know that this is in the set of, they told us in the basis there. And then since this does, if I apply rule 1, just throw a 0 on this. Now that's just the 0 string, right? Just the string of length 1 with 0. This belongs to the set of strings. If I apply rule 2 and just pop a 1 onto it, This is just the string called 1. That belongs to the set of strings. And now that this belongs to the set of strings, I just throw a 0 on it. Apply rule 1 again. This would belong to the set of strings, 0, 0. Apply rule 2 to it, just throw a 1 on it. This belongs to the set of strings. Same thing for this 1. 1 belongs to the set of strings. Apply the rules. If I apply rule 1, then 1, 0 belongs to the set of strings. Apply rule 2, put a 1 on that, and 1, 1. That string belongs to the set of strings. Those are all the strings of length 2. And then I keep building. 0, 0, just apply the rules. You get 0, 0, 0, and 0, 0, 1. Those are strings. These both belong to the set of strings. To this element 0, 1, right? Just apply the rules. 0, 1, 0, the first rule. 0, 1, 1, the second rule. There's some more strings of length 3. 1, 0 belongs to the set of strings. So again, applying the rules, you got 1, 0, 0, 1, 0, 1. Those belong to the set of strings. Then apply the rules to 1, 1 here. You got 1, 1, 0, 1, 1, 1. Those belong. And there's your 8 strings of length 3. And then I apply it to 0, 0, 0. You'd get 0, 0, 0, 0, 0, 0, 0, 1. Then apply the rules to 0, 0, 1. You get 0, 0, 1, 0, 0, 0, 1, 1, right? And so on. And I could do this forever. Right? Do this all day long. Keep building and building and building these longer and longer strings just by applying these couple rules to elements that I previously had. All right. So they show you here, maybe a little simple. So here, how many applications of the recursive rule given in the definition above are required to construct the string 1? Well, I just showed you. You take the lambda, you take the empty string and apply rule 2 to it. So you're only doing one application of the rules. And really just however long the string is how many applications of the rules you're going to use, or how many times you're going to use a rule. Here, I'd add 1, add 1, add 0, add 0, add 1. That's five applications of the rules. So really the number of applications of the rules is how long the string is. All right, and here it talks about talking about the length of a string. Right? Remember so the base case, the length of the lambda, the length of the empty string is 0. And then a recursive rule to give you the lengths of future strings. If a string belongs to the set of strings, then the length of that string with 0 on it is the length of that string plus 1. Right? Because you just take the length of the previous string and you're adding a 0, so you're increasing the length by 1. And the length of that string with the number 1 put onto it is the length of that string plus 1. Right? You just when you add 1 onto it, you're increasing the length by 1. Now this is kind of a joke here, but what's the length of the string 0, 0, 1? It's 3. But if I applied this recursive rule, it would be the length of 0, 0 plus 1. And the length of 0, 0 would be the length of 0 plus 1. And then the length of 0 would be the length of the empty string plus 1. And you end up with 1 plus 1 plus 1. 0 plus 1 plus 1 plus 1 is just 3. I mean, again, it's silly. But you see I went back and did all that. Showed you the recursive rule. And if the length of some string x is 7, then if I add 0 on, it's going to be length 8. Right? Real simple stuff. All right. Then here's a recursive. I say recursive definitions for functions, recursive definitions for sets. Here's a recursive definitions for pictures, graphs, a special kind of graph called a perfect binary tree. So the next example is a recursive definition for a set of mathematical objects that are not strings or functions. A tree is a kind of graph, right? We've seen directed graphs before, right? Digraphs. This is a little different. A tree has vertices, right, denoted by some dot or a circle, and edges, denoted by segments, right? Just like any other graph you've seen, only they're not directed, right? There's no arrows, which connect pairs of vertices. Not every collection of vertices and edges is a tree. A formal definition of trees, along with their properties, is given elsewhere in this material. Actually, it's not until chapter 14 that we're going to see the formal definition of a tree. Right? But here, they give a recursive definition for a particular type of tree, a particular class of trees called perfect binary trees. All right, so each perfect binary tree has a designated vertex called the root of the tree, right? And then the trees get built from there. All right, so here's the definition, the recursive definition of a perfect, the set of perfect binary trees. What are considered perfect binary trees? Now, the basis is just a single vertex with no edges is a perfect binary tree. Right, so just a circle or just a dot. The root is the only vertex of the tree. All right, the recursive rule. So if T is a perfect binary tree, then a new perfect binary tree T prime can be constructed by taking two copies of T, adding a new vertex V, and adding edges between V and the roots of each copy of T. The new vertex V is the root of this new tree T prime, and they show you here, and I will show you examples. I will show you how these perfect binary trees are built using the way they describe this rule here. Right. So again, the most basic, that basis they gave us, all right, so we're talking, so again, I'll let S be the set of all perfect binary trees. Now the basis, with just a vertex, that is a perfect binary tree, the most basic one there is. Now, here's what the rule was. If you have a perfect binary tree, how do you construct more? This is what the recursive rule tells us. It says you take that, make two copies of it. So this one was just a single dot. Right? Then create a new vertex above it, call it that V now, and connect to the roots of the old ones. So here's another perfect binary tree. And then again, I'm going to apply the recursive rule to this. So here's a perfect binary tree, this picture here. I make two copies of it, which is just one node up top, two nodes, two vertices in the bottom like this. There's one copy of that picture. Here's another copy of that picture. And I put another vertex above it, call that V, and connect it to the roots of the other copies. Right? This is another perfect binary tree. Right. And then again, taking this perfect binary tree, I'll apply the rule one more time because there'll be a lot of drawing. So I'll make two copies of this. So here, I'm going to make it a little smaller. So there's one copy of this tree here. Make another copy. And then, so there's my two copies of this tree. Put up another vertex, call it V, and then connect it to the roots of those previous copies. And here's another perfect binary tree. Right, now what you're going to notice about these binary trees, these perfect binary trees, is that at every level, the number of vertices, the number of circles, dots, is just a power of 2. See how there's 1, that's 2 to the 0. Then 1, then 2, that's 2 to the first. And then you see 1, then 2, then 4, 2 to the second. 1, 2 dots on that level. 4 on that level, then 8 on that level, 2 to the third, right? So the number of dots every level doubles in a perfect binary tree like this. And then if I wanted to make another one, I'd make, again, 2 copies of this and connect it to a vertex, right? Connect the roots to another vertex. All right, so that's what this rule is telling us to do. And I go through an example here. I already showed you this, right? How we build perfect binary trees. All right, now how many steps are needed of the recursive definition here? None. That was the basis. Right, that was the basis. And if you noticed, every new level that gets added was another step. Like I would, to make this one, I'd apply it once. Make these, I'd apply it twice, right? Because there's 2 more levels added to that root. However many levels are at, there's no levels beneath the root here, so I didn't apply the recursive rule. Here there are 2 levels underneath the root, so I would have applied that rule twice to make that kind of a tree, and I already made that picture on my paper. All right. And then you have a challenge activity. There's only 3 of them, where you're given a recursive definition of some sort, whether it be a recursive definition of a function like I have here. And then here, what's the value of f of 3? Now remember, this is that floor function. Remember the little notation for the floor. So f of n is the floor of f of n minus 1, right? The previous value divided by 2, and then plus n squared. And this is for values of n greater than or equal to. And they want f of 3. So I'm hoping you could do that. Find f of 3. This level. Again, they give us a recursive definition. Now, so here S is a set of arithmetic expressions recursively defined as follows. So the base case, every variable from the set, A, B, C, D, E, F, is an S. So all these variables are an S. All these expressions, A, B, C, D, and F, are an S. The recursive rules: if you have variables in S, expressions in S, then adding them is also an S, multiplying them is also an S. So which of these expressions would be an S? Let's see, A times B times C, yeah. Because A and B are an S, so A times B would be an S. C is an S, so then A times B times C would be an S. C plus D would be an S, and then A is an S, so the product of these would be an S. A plus B times C, yeah, B times C would be an S. A is an S. A plus B times C would be an S. Heck yes. A times D is an S, sure. C times B. Although based on the way it's written, I don't know about the parentheses. Because if you really specifically go by this, only when things are added, parentheses are put in, and when things are multiplied, they're not. So I'm going to keep it this way. Okay, so maybe, oh yeah, this one isn't, because I just said it. I just said it. B times C wouldn't have parentheses around it. Yeah, so again, really pay attention to how the rules define. So let me see another one like this. So yeah, so this one, A plus B, when you add, parentheses get put together, multiplying, no. So this one's okay. This one though, if I add A and B, there'd be parentheses around that. So it'd be A plus B with parentheses around it, and then plus C. So this one couldn't be made. A times B is fine, A times B times C is fine. Yeah. See, this could not be generated again but if you use the specific rules applied, right? Pay attention, like I did on the first one. All right, let's see what the third level looks like. And here, S is a set of strings with A's and B's in it instead of zeros and ones. And then B belongs to S, and if two strings belong to this set, then X, A, Y belongs to this set. That's the only rule. So it says here, list all the strings of length 3. Let's see. B is the only, so the base case is in there. B belongs to it, that's it. So since B is the only one in there, BAB would be a string of length 3, BAB, comma. And man, that would really be it, wouldn't it, for strings of length 3? Because all we know from the beginning is that B is in it. Now we know that then BAB would be in it. That's of length 3. And then BAB, A, BAB, BAB, AB, right? B, A, BAB, yeah, and nothing else would be, everything else would be longer. Yeah. Yeah, but yeah, pay attention again to how the rule is defined to be able to construct other elements of the set. All right, and then you have your additional exercises. Again, some of these are assigned, some are not. I would still recommend going through all of them, you know, just to get more exposure to the material, get more practice. And you got the solutions to look at if you want, but please try to work things out, try to work problems out before you look at the solutions. You know, you're not going to learn much of anything if you're just copying solutions down. So hopefully this video helps you when you're, you know, working through this kind of this section on your own. If you have any questions at all, of course, send them my way. And thank you very much for watching.